In the previous lecture, we established that the molar ratio coefficients in a balanced chemical equation give the ratios between the reactants that ensure that reactants are completely used up and turned into products. They also give the ratios between the amounts of reactants used and the amounts of products formed. However, what happens if there is not enough of one reactant to completely react with another? Let's consider the same example as in the previous video, the combustion of methane. The balanced chemical equation for this reaction tells us that methane and oxygen should be taken at a 1 to 2 molar ratio in order to completely use up the reactants. In other words, that for each methane molecule, 2 oxygen molecules must be taken. As a result, pair every 1 methane molecule and 2 oxygen molecules that are reacted, 1 carbon dioxide molecule and 2 water molecules are formed. Let's say that we have 3 methane molecules. To completely react them with oxygen, we would need twice as many, 6 oxygen molecules. But what if we only had 4 oxygen molecules? 1 methane molecule would react with 2 of these oxygen molecules, forming 1 carbon dioxide molecule and 2 water molecules. The second methane molecule would react with the remaining 2 oxygen molecules, forming a second carbon dioxide molecule and 2 more water molecules. However, at this point, there would be no more oxygen left. The third methane molecule would thus be left unreacted. There wouldn't be enough oxygen to burn it. The reactant, the amount of which is insufficient for using up the other reactants and completely converting them into products, is called the limiting reactant. In our example, there isn't enough oxygen to completely burn the available methane, so oxygen is the limiting reactant. Let's now consider the following situation. We have 2 methane molecules and 6 oxygen molecules. Each of the methane molecules reacts with 2 oxygen molecules, so that overall 2 carbon dioxide molecules and 4 water molecules are formed. However, 2 oxygen molecules remain unused. In this scenario, methane is the limiting reactant because there isn't enough of it to completely use up all oxygen. In both cases that we considered and in general, the limiting reactant is the reactant that is used up completely when some amounts of the other reactants still remain. The theoretical yield of a product of a chemical reaction is the amount, that is the number of molecules or moles of that product, that can be built with the given amounts of reactants. The theoretical yield is determined by the availability of the limiting reactant. In our first example, where 3 molecules of methane and 4 molecules of oxygen were available for the reaction. The limiting reactant was oxygen. From the balanced chemical equation, we know that for every 2 oxygen molecules reacted with methane, 1 carbon dioxide molecule and 2 water molecules are formed. Because the limiting reactant is used up completely, we find that the number of CO2 molecules formed is 1/2 of the number of oxygen molecules available, 2. And that the number of water molecules formed is the same as the number of oxygen molecules available, 4. Therefore, the theoretical yield of carbon dioxide is 2 molecules, and the theoretical yield of water is 4 molecules. Note that the theoretical yield is calculated for each product separately. Of course, we very rarely deal with amounts of reactants and products as small as in the examples we considered. However, when these amounts are much larger and are specified in the number of moles rather than number of molecules, the same reasoning applies. Remember that the mole is simply a unit for counting very large numbers of objects, typically atoms and molecules, and that each mole contains the same number of objects, 6.022 times 10 to the 23rd power. So if 3 moles of methane and 4 moles of oxygen were available, oxygen would still be the limiting reactant. We need twice as much oxygen as we have methane to burn methane completely. The theoretical yield of carbon dioxide would be 2 moles, 1 mole for every 2 moles of oxygen, the limiting reactant. And the theoretical yield of water would be 4 moles, 1 mole per every 1 mole of oxygen reacted.